In this video, we're going to talk about solving matrix ODEs when the matrix has complex eigenvalues. So we begin in the normal way. Our first step would be to find the eigenvalues of the matrix, and then to find the eigenvectors. So let's look at the characteristic polynomial. So we look at determinant of A minus lambda I. So I'm taking a determinant, so I'm going to write my vertical lines to indicate I'm taking a determinant. So when I subtract lambda from each of the diagonal entries, we get negative lambda and negative lambda on the diagonals. The other diagonal entries are the same, so negative 1 and positive 1. And now taking the determinant, first we multiply the two negative lambdas. That'll give us lambda squared. And then multiply the 1 and the negative 1. So that's negative 1. But we subtract that. So we subtract negative 1, which is lambda squared plus 1. So lambda squared plus 1. So that's our characteristic polynomial. And now we form the characteristic equation by setting this equal to 0. So set lambda squared plus 1 equal to 0. And if we isolate for lambda and square root both sides, we'll get that lambda is plus or minus I. All right, so we have some complex eigenvalues here. So we have some complex eigenvalues. So up until this point, when we've seen complex eigenvalues, we've typically said, oh, we're not going to worry about this situation. This is when we're finally going to talk about it more in detail. How do we handle complex eigenvalues? Now we actually want to work with them. All right, so even when we have complex eigenvalues, we can still go ahead about finding the eigenvectors in the normal way. So next, let's find the eigenvectors. So find the eigenvectors. So let's look at each eigenvalue one by one. So one of my eigenvalues is lambda equals I. So I take that eigenvalue and I form A minus I times the identity. All right, so when I form this matrix, we get the matrix that has negative I and negative I on the diagonals, negative 1 up here, and then 1 down there. And now we want to row reduce this and find the null space like we normally would when we're trying to find eigenvectors. So the first thing I'll do is, I would like the 1 to be up in the top left. So let's switch row 1 and row 2. Having the 1 in the top left is just going to make the computations a little bit easier. So let's put 1 negative I in the first row and then negative I, negative 1 in the next row. So now what we want to do is we want to zero out this negative I. To do that, we'd multiply the top row by I, so I times the first row, and add that to the second row, and insert into the second row. Okay, so when we do this, multiplying that top row by I, we'll turn the 1 into I, and multiplying negative I by I will give us negative I squared. But I squared is negative 1. So negative I squared is positive 1. All right, so when we do this, now we are adding I to the negative I, and that'll give us a 0 down here. And we're adding 1 to the negative 1, and that will give us a 0 down there. And the first row stays the same as 1 and negative I. Okay, so now we're ready to write down the equation for this row. So we'd have x1, and then if I move the negative I over the right-hand side, this would be equal to I times x2. All right, so we are ready to write down our eigenvector. So x1, x2, if I write it as a vector, so x1 we know is I times x2. And x2 is free here, so we leave that how it is, x2. And then we can factor out the free variable and get x2 times the vector I1. And now I could form my eigenvector. So I'll call this v1 for my first eigenvector. So maybe I'll let x2 be 1. And if we do that, we get I1. We can basically let x2 be whatever we want as long as it's not 0 and get an eigenvector. All right, so we have an eigenvector that goes with this eigenvalue, lambda equals I. Now I need, let's talk about what the eigenvector would look like for the other eigenvalue, negative I. And it turns out there's an important shortcut to getting that eigenvector. So first I want to recall some terminology from algebra. So the numbers I and negative I that we got for our eigenvalues, these are called conjugates. Or sometimes we call them complex conjugates. So in general, conjugates are pairs of complex numbers, one that looks like a plus bi, and the other one that looks like a minus bi. So I and negative I are examples of complex conjugates. All right, usually we'll just call them conjugates though. All right, so here is the key fact. So the eigenvectors of conjugate eigenvalues, like I and negative I, are also conjugates. So that'll greatly reduce the time it takes us to find all of our eigenvectors. So for example, in our problem, if we looked at the other eigenvalue, which was negative I, its eigenvector, which I'll call V2, if I want to get it really, really quickly, I just take the conjugate of the other eigenvector that I had for positive I. So the conjugate of I1 would be, when I take the conjugate, I switch the sign of the imaginary terms. So I switch it on the I, and I'd get a negative I. I don't switch it on the 1 because the 1 is real, so that stays. And that's actually an eigenvector for lambda equals negative I. So that's pretty nice. That gives us a quick way to get the eigenvectors when our eigenvalues are complex conjugates. All right, so at this point we have our eigenvalues and eigenvectors. So we can form our general solution. Okay, so I'm calling this a general complex solution because it involves complex numbers. So x of t will be equal to c1 times e to the first eigenvalue times t, so I times t, and then times its corresponding eigenvector. So the eigenvector that we got for this was I1, and then plus c2 times e to the other eigenvalue is negative it, times its corresponding eigenvector, which was negative I1. So that is a general complex solution. Just like when we talked about second order ODEs and we got complex roots to our characteristic equation, we want to be able to find real solutions, even when our eigenvalues are complex. So our goal now is, well, we want to find real solutions. Okay, so how do we do that? What is the idea? So if we want to find real solutions, so I'm going to break this up into steps. Okay, so the first part of the idea is, well, we take one complex solution in a conjugate pair. So whenever we have a conjugate pair, like we did in this problem, with eigenvalues I and negative I, we just take one of their solutions, because the other one is really closely related to the first one, and it turns out just taking one of them will be enough to actually find real solutions that correspond to both of them. All right, so in the context of our example, so e.g., if we look at e to the it, and then times its eigenvector I1, so this was the conjugate pair that's associated with lambda equals I in our problem. Okay, so let's do this. So next what we're going to do is we're going to use Eulers formula on this, on the e to the it term. So part 2 of the idea is, now let's use Eulers formula to break this into its real and imaginary parts. So let's just remind ourselves what the complex solution we were looking at. So we were looking at e to the it times, and the eigenvector was I1. All right, so let's see if we can rewrite this. All right, so if we take this, we can use Eulers formula on the e to the it term. So we're going to use Eulers formula. Eulers formula. And doing that, the e to the it becomes cosine of t plus I sine t. All right, and we can also split up the vector I1 into its real and imaginary parts. So the real part of this would be the vector. I know it's definitely going to have the 1 because the 1 is real, but the first entry doesn't have any real part to it. So I just write 0. And then I'll put plus I times all the coefficients of I. So in the first entry, that's a 1. The second entry didn't have any i's, so its coefficient would be 0. Okay, so for my eigenvector, we've split that up into its real and imaginary parts. For this e to the it, the part that had the eigenvalue, we've used Eulers formula on that. So Eulers formula applied to this e to the it term. All right, so now let's continue to simplify this. So the next thing we'll do is we'll distribute everything out here, or we will FOIL everything out. So doing that, we get cosine of t times the vector 0, 1. And if we multiply I sine t times this last term, I1, 0, we get, so the I squared becomes negative 1. So we have negative 1, which we don't actually need to write. We can just write negative sine t times the vector 1, 0. Okay. And now let's multiply the other pairs. So from multiplying I sine t times the vector 0, 1, and from multiplying I1, 0 times cosine t, each of those terms will have an I in it. So let me just factor that I out. All right, so we get sine of t multiplied by this vector. So sine of t multiplied by the vector 0, 1. And we also get an I term from multiplying this last term, I1, 0, times cosine t. So I'll write plus cosine t times the vector 1, 0. All right, so that's what we get when we distribute, or we FOIL out. So now we can identify what the real part and the imaginary part are. So the real part is this. So this is the real part. And the imaginary part is sort of the coefficient of I. So that is all of this. It doesn't include the I, it's just the coefficient of it. So this is the imaginary part. Okay, so if we write both of these in a more condensed format. So the real part, if we were to distribute the cosine t in and the sine of t in, and then combine these two vectors by subtracting them, the first entry ends up being 0 minus sine t. So that's negative sine t. The second entry ends up being cosine t minus 0. So that's cosine t. So that's our real part. It's this vector. If we do the same type of thing for the imaginary part, the first entry would be, I get 0 plus cosine t. That's cosine t. And then sine of t plus 0. And that's sine of t. All right, so we got the real part, we got the imaginary part. So this brings me to our key fact. So the key fact is the following theorem, which says that the real and imaginary parts that we get when we do this process are always going to be two real, linearly independent, and that's the really important part. They're going to be linearly independent solutions. So this real part and this imaginary part, they are now two real linearly independent solutions. So because we have two of them, we are ready to write down our general real solution. So that would look like x of t is going to be equal to c1 times our first real solution, which was negative sine t cosine t, plus c2 times the second real solution, which was cosine t sine t. And that is our general real solution right there. So one key thing that I want to point out about this before we do another example is to notice that when we wrote our solution in terms of complex numbers. So let me scroll to that. So in terms of complex numbers, sorry, let me just scroll. So with complex numbers, here was our general complex solution. So each eigenvalue, like I and negative I, along with their corresponding eigenvectors, sort of contributed a linearly independent solution. So here, our matrix A was 2 by 2, and we had two distinct eigenvalues. So we had two linearly independent eigenvectors, and that's why we had two linearly independent complex solutions here. So when we have a conjugate pair of eigenvalues, when we try to find real solutions, a conjugate pair means there's two of them. So when we did this process of finding real solutions, we needed to get two linearly independent solutions. And we have done that. We found two real linearly independent solutions. That's what this whole thing with doing Eulers formula to split our conjugate solution, our complex solution into the real and imaginary parts does. It takes our two complex solutions from the conjugate pair and it replaces them with two real solutions. Okay, so this will apply even when we have more solutions because our matrix is larger. All right, so let's do another example. So let's find the general solution of this matrix ODE where A is 2 by 2, and we're given that it has the eigenvalue 2 plus 3i that corresponds to this eigenvector v1. So at this point, pause the video for about 3 minutes, maybe 2 to 3 minutes, and try this question. So 4, 3, 2, 1, pause the video. Pause the video and try this for about 2 to 3 minutes. All right, so hopefully you did that. Hopefully you've paused the video and tried this for about 2 to 3 minutes. All right, so I'm going to want to find real solutions to this. We're going to want to find real solutions to this. All right, so to do that, just for a little bit of review, actually before I get into the review, there's one other thing I wanted to mention about A. So A, we want to assume that A has real entries. So if A has real entries, that means its eigenvalues come in complex conjugate pairs. So when we have complex eigenvalues, they will come in conjugate pairs. So this means that lambda equals 2 minus 3i is also an eigenvalue. Okay, and then its eigenvector, which I'm just calling E-vec, so v2 would be the conjugate of this eigenvector. So this I would change to a negative I, and in the next entry, the negative 5i would become plus 5i. So that would be the eigenvector that goes with this eigenvalue. All right, so we want to find real solutions now. And actually, before I do that, let me just briefly comment on this thing that I added about A. So I said A has real entries. I need that condition to guarantee that my eigenvalues occur in these conjugate pairs whenever they're complex. Because if my matrix A has real entries, that means its characteristic polynomial is going to have real coefficients. And if it has real coefficients, part of the fundamental theorem of algebra tells me that when there are complex roots, they occur in complex conjugate pairs. But if my polynomial was allowed to have complex coefficients, then my roots don't have to occur in these conjugate pairs. So this is actually really important that my matrix has real entries here. Otherwise, I don't know that my eigenvalues, when they're complex, are in conjugate pairs. So if I want to find real solutions, whenever we have these complex eigenvalues, we take one solution in a conjugate pair. So for example, if we were to take lambda equals 2 plus 3i, and then form its solution, that would look like e to the 2 plus 3i, and multiplied by its eigenvector, which was I 4 minus 5i. Okay, so I just have to take one solution in a conjugate pair. I don't have to do both of them. All right, so now what we want to do is break this up into the real and imaginary parts with Eulers formula. All right, so let's use Eulers formula on this. So if we do that, if we use Eulers formula on this, we will get, so first off, e to the 2 plus 3i becomes, this becomes e squared times e to the 3i. And then I have that times the vector I, and then 4 minus 5i. All right, so we have this. Now let's use Euler's formula on the e to the 3i term. So we have e squared, and then using Euler's formula on that, we'll get cosine of 3t plus I sine of 3t. I'm realizing now that there's something important that I forgot to write. So this 2 plus 3i should be multiplied by t. So I forgot that t. Let's go ahead and add that in. So when I first split this up, we'd have 2t and then 3it here. And then I would have an e to the 2t here. Okay, so now I think this looks good. So if you're worrying what I was doing before, okay, so I think I fixed it now. Okay, so we still have this vector here, and let's split up that vector into its real part and imaginary part. So the real part would be 0, 4, and the imaginary part is I, so well, we have I multiplied by 1, negative 5. So the 1, negative 5, that's the imaginary part. So just like before, we want to now distribute this out. Okay, so let's keep the e to the 2t out in front. So e to the 2t out in front. Okay, so if I distribute this, we get cosine of 3t times the vector 0, 4. So I'm going to write everything that's real first. The other real term we get is by multiplying the I sine term with this I vector term. So multiplying those, I times I will give us negative 1. So I could just write negative. So negative, and then we have sine of 3t times the vector 1, negative 5. So those are the terms that contribute like real values. And now the other two pairs that I multiply give me an I. So I'll have I times, so I get something from multiplying sine by the vector 0, 4. So sine of 3t times the vector 0, 4. And we also get an I term by multiplying cosine of 3t times the vector 1, negative 5. So cosine of 3t times the vector 1, negative 5. So close that parentheses, and now I think I closed the big bracket. Yeah, so this bracket that I'd open up, now we go ahead and close that. Okay, so we are ready to now write down the real part and the imaginary part. All right, so the real part. So the real part of this is, so the stuff that doesn't have the I, but we got to remember that this e to the 2t is also part of it. So if e to the 2t distributes in to these first two terms, the type of thing that we'll get is, we'll get e to the 2t in the first entry, multiplying, so the cosine times 0 is 0, and then I get minus sine times 1. So that would give us minus, and then we'd have the sine of 3t. So that's what I get for the first entry. The next entry, well, let me not multiply the e to the 2t in just yet. So I get 4 cosine of 3t, and then we get plus 5 sine of 3t. But that whole thing now gets multiplied by e to the 2t. So this whole thing gets multiplied by e to the 2t. And that is the real part. Let's write down the imaginary part. So the imaginary part is also going to be a vector. So I am also going to have to distribute e to the 2t into the imaginary portion. But let's focus on what we get when we combine these sine and cosine vectors here. So the sine times 0 is 0. And then plus this cosine term would be, I would get cosine of 3t. But that's going to get multiplied by this e to the 2t. So we'd get e to the 2t times cosine of 3t. All right, so for the next entry, we would get 4 sine of 3t. And then we'd have minus 5 cosine of 3t. So that whole thing needs to get multiplied by this e to the 2t as well. So we get e to the 2t times that. And that is our imaginary part right there. Okay, so we got the real part. We have the imaginary part. So finally, we are ready to write down the general solution. So we now have two linearly independent real solutions. Okay, so our general solution will look like C1 times this first solution. So that's what we have here, C1 times that first solution. And then plus C2 times this second solution. So that is our general real solution. So again, the key ideas to get this when we had these complex eigenvalues was, so as long as our matrix had real entries, these eigenvalues occur in conjugate pairs. So anytime we had a conjugate pair, we took one solution in that conjugate pair. And that's what we did here. And then we broke that up into real and imaginary parts using Eulers Formula. And then the real part and the imaginary part of Eulers Formula, they became two real linearly independent solutions. And I include those in the general solution.